So continuing our discussion about new terminology and ways of describing graphs, and along with the boards going up in Jason's room, we need to create some definitions for some graph parts or concepts about graphing. So first, we want to look at or be able to evaluate by looking at a graph where a graph is increasing. So in the case of a parabola, and let's give this a vertex, say -2 and 4. We can tell by visual inspection that the graph is increasing from -infinity all the way up to 4. And that the graph is decreasing from 4 to -infinity. But having said that, we know that the highest value that it's going to achieve is 4. But we don't actually talk about intervals of increase by talking about how far or how high it goes. This already has a language for it. This would be the maximum. So the maximum for this graph would be 4, right? So the maximum value. And that's just more Algebra 2. We've done that before. But whenever we want to talk about a graph where it's increasing, we're going to talk about the actual interval. So right here at -2, this is going to be the interval at -2 all the way backward to infinity, where this graph is increasing. So the interval of increase, and this was badly written, let me do it again. Feeling a little cramped for time based on the noise next door. I feel like if I rush, you're not going to hear it. So from -infinity to -2 would be the interval of increase. And then on the other side, we're looking at an interval from -2 to infinity, which would be the interval of decrease. And then there's a whole bunch of mathiness in your text. A function is increasing on an interval if for every point on that interval the function of 1x is strictly less than the function of the x value right next to it. So that looks like mathy gobbledygook. It's actually a beautiful work of art because math is. But what it means is we know on an interval that the function is continuously increasing on that interval if every infinite time you choose some value of x for an input, that the output is strictly less than the next value. Not equal to, but strictly less than the next value. Same thing occurs for the interval of decrease if for every point on the interval the f of x1 is strictly greater than the f of x2. And then there's another idea, that is, if for every x on an interval the output is equal to the output of the x right next to it. And so on a graph that would be a constant part. So I could say, if I were looking at, say, this graph, right, I'd be able to say that the interval of constancy would be, in this case, let's call this x equals -9, and here x equals +5. So the interval of constancy would be -9 to +5. And so that would be a constant interval. So we have 3 things that can happen to a graph, and we have 3 new ways to describe something that we've seen before. Graphs decrease, meaning as you choose x values in the positive direction, the y values are going down. We have constants in a on an interval, which means every time you choose a greater x value, you get the same exact y value. And we have intervals of decrease, which means every time you choose a greater x value, you get a smaller y value. Okay, but bunch of language just to say something that you already know, but it's language that's very important in your future. Another idea that we need to look at and have a language for on a graph is, as graphs have kind of strange, unpredictable shapes, we don't have parent functions to define them, so we have to be able to describe them based on their new shape. And so in this case, and let me curve back around again and go up. Okay, so if you look at this graph, you can see that something important that's happening is you have right here, you have a place where the graph is lower. It reaches a lowest point and then it turns around and goes back up. Same thing here, you have another one. So unlike in a parabola where we can talk about the minimum or the maximum value being these areas, in some of these graphs we don't have just one minimum. We actually have two lower values, so we need new conversation to be able to talk about those. And similarly, we have two maximum or higher values. Now, it should be said that even though this goes off to infinity, it's useless to call this an absolute or some kind of a maximum, right? So we don't actually call this a maximum if the endpoint goes off to infinity. And on the other side, we don't call this a minimum. I mean, clearly it is the absolute minimum of this graph because negative infinity is the absolute minimum, but it's not useful to us. So we just call that approaching infinity. We use in behavior language to talk about that. But in this case, we need words to describe these. So I know that this is a minimum, so I can call it a min. And I know that this is also a min. But I have the further language of being able to identify this on the minimum on the right-hand side as the absolute minimum. So that's the absolute minimum on this graph, disregarding, of course, the endpoints because it's meaningless to call them minimums and maximums. And this one, the other minimum or any other minimum, is just called a relative. I've also heard them called regional minimums, and it just means that in relative to all the points around it, it's a minimum, but it is not the minimum of the entire graph. And so the maximum is the same. I have a relative maximum and I have an absolute maximum. And at this point, we only find these values by looking at a graph or a table in the same way we have found other values. All right, so we've talked about extrema. Now we have to talk about average rates. Now you've heard average rates before, but let's kind of talk about it specifically for PreCalc. An average rate of change can be identified as the slope of the secant line. So what does that mean? Well, first, suppose I want to find the average rate of change between this point and this point. So I don't really know what the points are. I mean, I don't really know how much I changed, and by rate of change I'm talking about the output rate of change. But what would the average be if I were able to take a rate of change all the way through this curve? If I were able to figure out the slope at every instant of the curve, what would the average slopes be? And you can kind of see that if I looked at a slope, say here, that just touches the curve, this is a negative slope, while here, this is a positive slope of almost exactly the same value, right? So I'm going to have negative contributors and positive contributors to whatever is happening on the output of this curve, but I can find the average. So after all of the counterbalancing has happened, I can find the average by actually just calculating the slope of this line, and the slope is known as the change in y over the change in x. We know that from the lowest level of algebra, but we're going to start now thinking of it as an average rate of change rather than as a slope of a line. So the slope of the secant line, by the way, a secant line is a line that intersects a graph or a region of a graph at exactly 2 points. Okay, so what we have is a line that intersects this graph, or this part of the graph. If I continued on, it would intersect at another point, but I'm really only concerned with these 2 points. So let's give our points some values. Okay, and now it's exactly back to Algebra 1. Change in y is y1 minus y2 over x1 minus x2. Let's call this P1 and this P2. So we have y2, oh, I did those backwards, didn't I? Not that it matters, but let's go ahead and keep consistent with our formula. So y2 minus y1. So y2 is 3 minus 5 over x2 is negative 2 minus 7. 3 take away 5 is a 2. Negative 2 take away 7, negative 9. And so my slope is negative 2/9. So the takeaway here is that the secant line is the line that intersects a curve at exactly 2 points, and that the average rate of change between those 2 points on a curve can be defined as the slope of the secant line.